Hey, let's go ahead. So we're gonna be doing PH 111. This is going to be chapter 7, which is gonna be your kinetic energy and work. Let's go ahead into the model. We opened up this from the module. And so supposedly, actually, let me just come over here. Supposedly, if I have a chair, let's say, I don't know if you can see me or not. Hopefully you can in this video. Let's say I got this chair over here. Let's say I take this chair all the way to the wall right over here and come back, which is about, I would say, 10 feet. Or should I take this chair, go all the way to that wall across from me, come back, which is about 20 feet. So my question is, which one did I do more work? The one that I go this distance, which is 10 feet, or the one I went that distance, which is 10 feet and came back? Well, your answer might vary. So the answer is gonna be both of them, we did no work. So because we came back to our same spot, we did no work. If I took this chair and I just moved it from this side to this side, which is about, I don't know, 2 feet over here, now you did work. You go back to the same spot, you did not do work. So which brings us to our definition of work. So the work done by the force acting on an object is equal to the magnitude of the force multiplied by the distance through the object's axon. So let me go ahead. So your work, and I'm just gonna say this is your work, is going to equal to the magnitude of the force multiplied by the distance to the force axon. So your magnitude of your force multiplied by your distance. Now, let me go ahead and mark this up. This is your force, and this is your distance. Now, in your book, you'll see it marked as S. So, same, I'll let you use D. So we're gonna be sticking for D for a second until I finish. Now, we defined your force as, from Newton's second law, as your mass times your acceleration, which makes the work equals MAD. That's why it's so important to get vacation when you have a job, to have vacation, because too much work will make you mad. Your mass times acceleration times your distance. Now, so your work is your mass times acceleration times your distance, which is your force times your distance. Now, in terms of units, your mass is in kilograms. Your acceleration, we define it as meters per second squared, distance over time squared, where your distance is in meters. Now again, we define, and from chapter 2, we define this as what? The Newton? Multiplied by your distance. So really, it's your Newton meters, which that's what we call a joule. We'll give it the big letter J. So your joule, that's gonna be your work unit. So your work is always in joules. Now it's named after James Prescott Joule, which he died in 1889. Now he did a little experiment where he got 2 small pebbles inside a container of water, and he put some weight on the other side. And what he noticed is when the weight goes down, when the pillows goes around, he noticed that the temperature raised up. So the friction heated at the water, and the same amount of work was always produced, the same amount of heat. So that brings us to the definition of energy. Energy is that property something has to enable it to do work. So you have more energy, you do more work. So your energy of a moving object is called your kinetic energy. Now we give it two words, KE. That's why I wrote down earlier your kinetic energy and work, I put KE. So now your kinetic energy depends on two factors, your mass and your speed. Your kinetic energy is going to equal to you 1/2 mv squared. So your KE, kinetic energy, equals to mv squared over 2. Or you can say something like saying 1/2 mv squared. And let me go ahead and write this down. That's your kinetic energy. So if I tell you what is the kinetic energy of a 1,000 kilogram car whose speed is 10 meters per second? So here's the example. Your mass was 1,000 kilograms and your speed was 10 meters per second, and you're looking for kinetic energy. And you know your kinetic energy is 1/2 mv squared, which is going to be your 1,000 multiplied by your 10 squared divided by 2. 10 squared is 100. So let me just write this down, times 100 divided by 2. Half 100 is 50, so that's going to equal to 50 kilojoules. Or you can say it's 50,000 joules. Let me just write this down. It would be 50 kilojoules. Okay, we got this one right. So now we need to find something called your potential energy. Now your potential energy is going to give it the letter PE. And this is your stored energy. Now your potential energy, examples for it is your gravitational energy, spring, electromagnetic, etc. Now you can change your gravitational to potential or potential to kinetic. You can go, and this is like a energy. Energy cannot be destroyed, it can be conserved, it can be converted from one form to another. So you can go from kinetic to potential energy, and from potential energy to work, etc. So let's go ahead and let me just write this down. Okay. So your potential PE, this is going to be your potential energy. Now, let's go ahead and watch our first video. So the question is, how high from that side we have to release the ball in order for it to escape? So, was it below the low side, equal to the low side, slightly above the low side, or much above the low side? Let's go right ahead. See this one? You just need a little bit on top of on top to get that little bit of energy in order for it to escape. So if we release that ball from that track, how high will it go on each side? So will be the steepest will be the highest, the least steep, the middle, or it's going to be all the same. 1, 2, 3. So let's say, the steepest, the middle, or the highest. Which one will it go in? They would say this is the highest, this is the steepest, this is the middle. So go ahead and lock your answer in. Let's go ahead and watch the video. Because it got the same energy in all three of them, so we'll go all the same height. Now let's take a look at another video. Now we both talked about the work, which equals your force times your distance. Let's take a look at the first one. So in this video, notice again, you got a certain amount of force and you're going a certain amount of distance. The more force the time you have with the force times your distance, the more work we're actually developing over here. So the more distance we go with that amount of force, your force times your distance, that equals to the work that we got. Now in the second video that we have, notice that we have a bigger force. So notice our work distance actually increasing on the same amount of distance from the first video, where, let's just see, we just had like this much work done on this distance. Same thing, you got 1, 2, 3, 4, 5, 6, 7. Let's say you go 7 units, and your end of your force, because you have more force, your end work is actually more. Now, with your work done at a slight angle, that's where your work actually decreases. And that's what we're actually going to be talking about, where your work is going to equal to your force multiplied by your distance, multiplied by your cosine, the angle that you're going in. So let me actually go do that one right now. So, okay, let me just see. So let's say, so we talked about how your work is going to equal your force multiplied by your distance. So if you have a resultant force, you're going in that way. Let's say you're this person right now over here, and you're traveling, and you got a suitcase that you're actually pulling. So you got your force coming in this way, which is a resultant of your F in the Y direction, F in the X direction, and F in the y direction, which from chapter 1, our math review, we looked at this is going to be your f, so this is going to be your f sine theta and your f cosine theta. So really your work is your force multiplied by your distance multiplied by cosine of the angle between them. So if theta was 0, that means your work, let's go work 1, is going to equal to, in this case, your force multiplied by your distance multiplied by your cosine 0 degrees, which cosine 0, again, you're going this way to 0 degrees, which is going to be your 1. So your work in this case is going to be equal to your force multiplied by your distance. Let's say you go backwards, you go at that 180. So when theta equals you 180 degrees, that means you work, let's say called W2. So what you're going to have, you're going to have F cosine theta, FD cosine 180, which is your cosine 180. That's going to be on the other side, so it'll be -1. So you work in this manner. Is going to equal 2 minus FD. That means your total work, which is going to be your first work plus your second work, which is going to equal to your FD minus FD, which is equal to 0. That's why when you have a distance, when you come back to the same distance, your distance work is going to equal to 0. So let's say we have an example. Find the work done if the force is 45 newtons and the angle is 50 degrees and the displacement is 75 meters. So let me come back over here. Let's do this example. So your force is 45 newtons and your angle theta is 50 degrees and your displacement d is 75 meters and you want to find the work, which again your work is your force multiplied by distance multiplied by cosine the angle. So that's going to equal to your 45 multiplied by your 75 multiplied by cosine 50. And this is going to equal to, okay, plug it in. Okay, I got 2,170 joules. Go right ahead. Yep, which that's what we got. Now, we're going to come back to potential energy in just a second. Now, your work, we said your work, too much work is important to take a vacation because too much work is going to make you mad. Your mass times acceleration times your distance, which again, this is derived from your work is FD cosine theta. And we're gonna assume that our theta is 0, so this is gonna equal to 1. So this is gonna equal to force times your distance. which again, your force is your mass times acceleration times your distance. Now, we introduced this kinetic equation from chapter 2, which is said our final velocity squared equals our initial velocity squared plus 2AD. Well, if we solve this to the acceleration multiplied by your distance, let me go ahead and label these first real fast. So this is going to be your distance. This is going to be your acceleration. That's your mass. And that's your initial velocity. And this is your final velocity. Now, solving again, going back, solving this for the acceleration multiplied by your distance, what you're gonna have? You're gonna have your VF squared minus your V naught squared divided by 2. Well, let's go ahead and plug that little fella in here. This. Let's go ahead and plug him in here. So what you're gonna have? You're gonna have your work, your network, is gonna equal to your mass divided by 2 multiplied by your V final square minus V initial square. Opening it up, what you get MVF square over 2 minus MV naught square over 2. Well, what a coincidence. This over here, ladies and gentlemen, this is going to be your final kinetic energy. And this one, this is going to be your initial kinetic energy. So, what we're saying is that your work is your kinetic energy final minus your kinetic energy initial, which is delta kinetic energy. Now, if you actually look at it at a broader view, so change in work is your force multiplied by your change of distance. But I'm going to go ahead, because we're going to be doing derivatives, I'm going to actually call this delta x, which is the same thing, displacement or distance. So let me just go so I can follow your book a little bit. So your delta work, your change in work is going to equal F dx. That means your work is going to equal to your limit from delta x to actually, let me just go limit. Let me go integration. Let me just go with integration from x2 to x1, L of x, d of x. Now, your vector f, we defined that I think in chapter 3, is going to be your forces in the x and the I direction, plus Fy in the j direction, plus Fk, Fz in the k direction. And we define the displacement distance r dr as dx in the I direction, plus dy in the j direction, plus dz in the k direction. Well, looking at the integration of dw, which is going to be f dot dr, which is going to be this one dot this one. What you're going to have? You're going to have fx dx plus fy dy plus fz dz. And again, we went through the dot product on the third chapter. So taking the integration for your work, what you're gonna have from your work from R1 to R2 dw, which is gonna be from your x1 to x2 f of x dx plus y1 to y2 f of y dy plus z1 to factor z2 f of z dz. But we've been talking about the x, so let's just take the x1. So let's take this little fellow over here. And we said your work, again, in the x direction be from x1 to x2 f of x v of x, which is gonna equal to your integration, your force again, your mass times x direction in the x direction, d of x. Well, if we take this term over here, so there's gonna be ma d of x, which is gonna equal to, now your acceleration, remember we talked about the acceleration before, which is your velocity over your time. So we can go ahead and pursue that. So this is gonna equal to your mass multiplied by dv over your dt multiplied by your dx. Well, now let's take dv over dt over here. Let's go ahead and change colors. So let's take this dv. So integration of velocity over time what's that going to equal to in terms of the distance x, h, your velocity over dx and dx over your dt. Which again, your distance over your time, that's actual velocity. So this is going to be your dv over dt, I'm sorry, over dx multiplied by your velocity vector, v. Well, plugging that back in, that means your mass times your acceleration times your dx is going to equal to your mass multiplied by your dd over your dx multiplied by your velocity vector v multiplied by your dx, which, what a coincidence, both displacements cancel out, leaving you with your mass times your velocity, dv, mv, dv. So your ma dx equals your mv dv. That means your work let me go ahead and get the black. That means your work change, which was your MADX from x1 to x2, we changed it. So right now, again, we go from velocity v1 to v2, mv dv, which is going to equal to your m integration v1 to v2 V dV. Solving this one, what you're gonna have? You're gonna have to mv squared over 2 you go from x1 to x2, so you're going from v2 minus mv1 squared over 2, which is we probably should have written initial final, which is the same thing as saying mv final squared over 2 minus mv initial squared over 2, which again, that brings us back to the conclusion that this is your kinetic energy final, and this is your kinetic energy initial. Let me change this to an I for initial. Which is going to be your delta KE, your change in kinetic energy. So again, your work is your kinetic energy final minus your kinetic energy initial, which is your change in kinetic energy. Go back over here. Then we have another question. So let's say it's accelerating at a rate of 1.5 meters per second squared. And the mass of the crate is at 120 kilograms, and it does not slip. The magnetic displacement is 65 meters. What is the total work done by the crate? So, let me go right over here. And I think this is example 3. So your acceleration is 1.5 meters per second squared. And your mass is 120 kilograms with a displacement D, or which is how much? I think it was 65 meters. And you want the total work. Now, again, we said your work is, and I think there was an angle. No, so it's going straight up and down. So your angle is going to be 90 degrees. So your work would be FD cosine 90. Which again, your cosine 90 is going to be 1. Now, we have the distance, we just don't have the force. Now, the force again is your mass times acceleration, which is going to, in this case, is going to equal to 120 times your 1.5. So it'd be 120 plus half of 120, 60, be 180 newtons. That means in this case, our work is going to equal to 180 newtons multiplied by your distance, which is your 65, multiplied by your cosine. I'm sorry, this is not 0, it's 90. It's not 90, it's 0. Again, you're going back and forth, so you're going in the 0 and 90. So this is going to equal to 1. So looking at this, so I got 12 joule, which is going to be 1.2 times 10 to the 4th power joules. So again, your work is your energy transferred by the force. Your energy is the ability to do work. Now, your work is your force multiplied by your distance, which too much work makes you mad. Your mass times acceleration times your distance. And we actually went through this equation where we developed what's the kinetic definition of the kinetic energy, which is your 1/2 mv squared, where your work is your change in your kinetic energy. So let's say we have a mass probe. So your mass of the space probe is 474 kilograms, and initial velocity is 275 meters per second. If 5.6 times 10 negative 2 Newton force acts on the probe to the displacement of 2.42 times 10 to the 9 meters, what is your final speed? So let's go ahead. This is example 4. So your mass, in this case, 474 kilograms with a 275 velocity. And with your force is 5.6 times 10 to the negative 2 newtons. And you got a displacement of 2.42 times 10 to the 9th power meter. And you want to find the final velocity. So this is going to be your initial velocity. Now, we said that your work, when we find out, so we're going to have to use the kinetic energy. So your work is your change in your kinetic energy, which is your kinetic energy final minus your kinetic energy initial, which is your mv squared over 2 final minus your mv squared initial over 2, which is going to equal to your f cosine theta multiplied by your distance d. Now, the satellite is actually going on the x-axis horizontal, so it's at the 0 degrees angle. So really, this little thing is going to go to 1. Rewriting this equation that we have, your force multiplied by your distance is going to equal to your mvf squared over 2 minus mvi squared over 2, which is going to be 5.6 times 10 negative 2 multiplied by your distance 2.42 times 10 to the 9th power is going to equal to, how much is our mass? 474. So the 474 multiplied by your v final squared, the one we need to find, divided by 2 minus your mass, which is going to be 474, multiplied by your initial velocity, which is 275 squared, divided by 2. So this is going to equal, so your final velocity should equal to close to 805 meters per second. Let's see if our answer is correct. Yep, we are good to go. Now, so let's talk about potential energy. We mentioned potential energy, which is PE, which is your energy that is in there. Now, So supposedly, let's say, let's say you have a basketball. Let's say you got a basketball. And let's say you got this basketball right over here. You go and you drop it. And let's say this is, let's say, hold up a second. Let's say this is the floor, right before it hits the floor. So let's call this your initial height, which makes this your final height. Now, the work done in this case with the act of gravity, because what it is, you got the gravity acting on it, on the ball, going down. Is going your force, again, we defined it as your force multiplied by your distance, which is again your your mass times acceleration mass, your distance. Now, what is your distance in this case? Well, in this case, your distance is your initial minus your final. Let me go ahead and define those. So this is your initial height. This is your final height. All right. So, which means that our work when it comes to gravitational, and this formula is going to equal to your mass times your gravity multiplied by your distance, which is your initial minus your final, which is going to equal to your mgh. And again, your acceleration, I forgot to mention this, is going to be your gravity, which is your 9.8 meters per second squared. The gravity acceleration, that's where we get the, I forgot to mention the g. So this is going to be your mgh naught minus your mgh final. Now, mgh, that's your initial potential energy. Final, that's going to be your final potential energy. That means your work, which is your change in kinetic energy, is going to equal to your change in potential energy. Your kinetic energy is going to equal to your potential energy. Now, the best example about this is a pendulum. So say you have a pendulum ceiling, and you have a little pendulum over here. Let me just replicate it. Go take it over there. Go take it over there. Now, when you probably see the pendulum, it goes back and forth. Now, when the pendulum is at the highest position, let's say over here, your potential energy is at highest. Your kinetic energy is at the lowest, probably closer to zero. So you're going from kinetic energy to potential energy back to kinetic energy. When it comes into this position, your kinetic energy is your highest, your potential energy is your lowest. Back to your potential energy at highest, kinetic energy is at your lowest. All right, so this is a movie over here on the module that would show the pendulum with the kinetic energy and potential energy. Now notice it's on the top over here, your kinetic energy is at lowest. potential energy at the highest. You have potential to do something. You haven't done it yet, but you have the potential to convert it to kinetic energy. This is your total work. Now, when it goes in, notice that your kinetic energy midway, your kinetic energy is the highest, your potential is the lowest. Same total potential, total energy, and then your total kinetic energy goes down, potential energy goes up, and vice versa. So let's say we have a question. You have a girl in the swing that's 2.2 meters above the ground. At the end of our motion, 1 meter above the ground is the lowest point. What is the girl's maximum speed? All right, so her initial height was 1 meter. Her final height is 2.2 meters. That means your displacement between them, your 2.2 minus 1, which is going to be your 1.2 meters. And you're looking for your maximum speed or your final speed. And again, your kinetic energy is going to equal to your potential energy because she's going on a swing. Go like this. Let's say this is a girl on the swing. And the swing is going back and forth. Where you get one over here, one over here, same as a pendulum. So your kinetic energy is going to equal to your potential energy, which again, your mv squared over 2 is going to be equal to your mgh. So solving for the velocity, your masses cancel out, so it's going to equal to your square root of 2 multiplied by g multiplied by h. So it'd be square root of 2 times 9.8 times 1.2. So we should get 4.8 meters per second. That's what we got. Let's do another example, shall we? Your gymnast that leads the trampoline at the initial height of 1.2 meters and reaches the maximum height of 4.8 meters. Before falling back down, what is the initial speed of the gymnast? Now, because he's going on a trampoline, his final velocity is going to be 0, and then when the initial velocity is going to be whatever it is. So he's going to go from initial to a 0 velocity. So let's go ahead and do this example real fast. It's going to be example 7. We'll switch to black. So your initial height is 1.2 meters, and your final height, which is going to be your 4.8 meters. And we're looking for your initial velocity, initial speed. Now you're knowing that final speed is going to equal be 0 meters per second. And again, your work, which is going to be your change in your kinetic energy, which is your mv final square over 2 minus mv initial square over 2. This is going to equal to, again, to your change in potential energy, which is going to be your mgh final. mgh initial minus mgh final. So let me go ahead and organize this. So for both of these, what you're gonna have? You're gonna have your mg, which is gonna go like this. Open them together, so bhi minus hf is gonna equal to, we said the final one is 0, so this is actually gonna go to 0. And what are we gonna have? If this one goes to 0, what you're gonna have? Minus mvi squared over 2. That means your initial velocity is gonna equal to, we can go ahead and cancel the masses out. Square root of minus 2g multiplied by your initial minus your final, which is going to equal to minus 2 times 9.8 times your 1.2 minus 4.8. Minus 2. I got almost 8.4 meters per second. That's exactly what we have. Now, let's talk about conservative and non-conservative forces. Actually, before that, let me just go ahead and write this down. So in order to transfer energy to an object, you have to extend a force on that object. So in order to transfer energy to an object, you have to exert the force on that object. That means your work again is your force multiplied this is multiplied by your cosine the angle between them. Again, F is the force, D is your distance, displacement. Just gonna call it displacement. And angle is the angle between them. So displacement while force is on it. So if you have your force again this way, it's gonna be your F sine theta. And this is your F cosine theta. The work is the amount of joules of energy given in an object or a system. Now your work is positive if the force gives energy. work is going to be negative if, I'm going to put this up, if the force is taking away energy. Now your net work is your first work, second work, third work, whatever it is. Which is, there's something called, which is gonna be your net force multiplied by your displacement. And then we'll talk about conservative and non-conservative forces. So your conservative forces, let's talk about conservative forces first for a second. Conservative work. So the work done by force depends on initial and final positions. So talking about conservative force, talking about your work done by force depends on the initial and your final position. So let's say if you have a box that's 5 kilograms, and let's say you move that box in 6 meters. That means you got your work going in this side, which your work is again your mass. Again, we're going down, so we're not going to worry about the angle. So be mass times gravity, which is going to be your 5 times 9.8. So we should get 49 newtons. This is actually your weight. Let me just go ahead and put it down weight. Now your work, which is again your force times gravity. So your work, you should get a different color for that. Okay, let me go ahead and erase this little fella. Now your work, you get a big W, which is your force times your distance, which is your weight, which is going to be your 49 multiplied by your 6 meters. So you should get B minus 300 minus 6 be 294 joules. So let's go. On the first try, you're going to take it down 6 meters. And then on the second one, you're going to take it up, the box up by 6 meters. And on the third one, you're going to take the box down by 6 meters. Then on the first one, your work, which is the one we just got, that's going to be 294 joules. On the second one, you're going opposite gravity. So for this one, opposite gravity, which means your work in this case is going to be minus 294 joules. On number 3, your work is going to go back at 294 joules. So conservative forces, the work done by the force depends on the initial and the final position. So conservative forces conserve mechanical energy. From their name, they conserve mechanical energy. The best example I really like to say about it is when you actually have a roller coaster. Go right ahead. And you're going back and forth, where your gravity work which is your mg potential energy H naught minus HF, where your H naught is going to equal to your HF. So your conservative force conserve mechanical energy. Now your non-conservative, let me go write this down. Your non-conservative force just like its name. This does not conserve mechanical energy. Where your mechanical energy is your potential energy plus all your kinetic energies. So let's say if you have an object, let me go right and get this. So you have an object, and you keep on moving that object back and forth, where you're gonna have your friction, F. So if you keep going back and forth, and the thermal energy what do you think is going to happen? If you keep on getting a box and you keep on going and moving it back and forth, what's going to happen? The thermal energy is going to go larger and larger. Now your work done by friction depends on the path taken. So basically, friction is not a conservative force. So for conservative, Your force K, because of the gravity, what you're gonna have potential energy, gravitational. Get a spring, potential energy, where spring. But when you have friction, and you have force associated with friction, are you gonna have potential energy because of friction? The answer is no potential energy associated with it, with friction. So, we talked about the spring force. Go ahead and label this. Which we defined it as your force times your distance, but in this case, it's gonna be something to be minus K multiplied by D. Now, the negative sign is because this force is going to be opposite of displacement. And again, when we got the box and we move it back and forth, the frictional force is going to be out, opposite sign. Let me get a different color on this. Your K, that's called your spring constant. And again, let me go ahead, go back to green. That's your displacement. So for a spring, along the x-axis, your fx is going to equal to minus k, and I would say x as your displacement in the x direction. So in this case, your work, which again is going to be F dt, we define the work from x1 to x2 or x initial to x final, whatever you want to call it, f of x d of x. For a spring, this is going to equal to your integration, again, from the initial displacement to the final displacement minus f of x dx, which if you plug in k of x, x dx. So that means your work done by a spring is going to equal to 1/2 kxi squared minus 1/2 k final square, which again, K is a spring constant. And again, the work can be positive or negative, depends on the energy transfer, like we said earlier. Let me actually go ahead and write that down. On the net energy. And again, where we said that is going to be positive. Yeah, it'd be positive if the force is giving the energy, and be negative if it's taking away energy. Now, we need to define something called power. So power is the rate of doing work. Now your power is the rate of doing work. Can write. So your power is how much work you can do per ton. Now, we defined your work as your Newton meters per time per second, which is going to be your joules per second. How many joules per second? We call that the watt, and we give it what W. So this is your unit for power. Now, so your average power is how much work with delta T. Or you can say that instantaneous power is dW over dt. Which, again, we solved this. So your dW is going to be your F cosine theta d, I'm just going to go with x, divided by dt, which dx, which is going to be F cosine theta dx over dt. So dx over dt, we defined that earlier as your velocity distance over your time. So your power is going to equal to V, the force multiplied by the velocity multiplied by cosine theta. And again, when you go on a 0-degree angle, so there's going to be your F dot V, which is a result of dot product, which is again your A dot B, your AB cosine the angle between them. So it'd be your F dot your V. Now, going back to the non-conservative force. So when we're talking about your non-conservative force, or work. It's going to be your change in kinetic energy plus your change in potential energy. In this case, you're changing your kinetic energy initial, your final minus your kinetic energy initial plus your potential energy final minus your potential energy initial. Well, let's go ahead and organize the finals and initials together. So what you're going to have, kinetic energy final plus your potential energy final minus your kinetic, let's go ahead and do this. Kinetic energy initial plus potential energy initial. Well, remember we defined the energy as your kinetic energy plus your potential energy. So this one over here, this whole first term over here, that's going to be your kinetic energy final plus potential energy final. That's going to be your final energy. This term over here, that's going to be your initial energy. That means your non-conservative work is going to equal to your EF, final energy minus your initial energy. So if your non-conservative work equal to 0, that means your final energy is going to have to equal to your initial energy. So if the network on an object by a non-conservative force is 0, then the energy do not change. So if the net work, let me just rewrite this as work. If the net work on the object by non-conservative force is 0, then the energy does not change. And again, let me just write this down, write that over here. Your work for the non-conservative, which is your EF minus your initial, which is again, opening it up, is your kinetic plus minus potential. Plus MGH final minus well, I'm going to go ahead and reorganize this. So let me just go ahead. this. We said is going to equal to 0. To 0. So that means your final energy is going to equal to your initial energy. That means your mv final squared over 2 plus mgh final is going to equal to mgh initial plus mv initial squared over 2. Now, if you notice that our masses can cancel out, so what we have left, we would have Vf squared over 2 plus GHF is going to equal to GHI plus MVI squared over 2. Oh, no M's. Have it. So let's solve this to, if you solve this to the final velocity, what you're going to have? You're going to have 2 multiplied by G, multiplied by the difference between them, initial minus your final, plus your initial velocity, and this was square root. So to find the final velocity is 2g, difference in height, plus vi. Let's go ahead and do an example on this one. The motorcycle is trying to leap across the canyon by driving horizontally off a cliff 38 meters per second. Ignoring resistance, find the speed at which the cyclist strikes the ground. So his initial velocity is 38 meters per second. And again, his energy before, his final energy is going to have to equal to your initial energy. And again, let me go ahead and write this down one more time. So what you're going to have? You're going to have mvf squared over 2 plus mghf equals mvi squared over 2 plus mghi. And you can cancel ahead the masses and solving it like we just did. What you're going to have? You're going to have the square root of 2 times g times h initial minus h final plus your initial velocity squared. So this is going to equal to your 2 times 9.8. Now, the height difference is given right over here. Is 70 minus 35. Let me go ahead and write this down. So HI is 70. H final is 35. From this one, your displacement is going to be 70 minus 35, which is going to be 35 meters. So this one's going to be 35 meters down here. Plus your 38 squared, that's all square root. Let me plug this in my calculator. And we should get 46 meters per second. Yep, we got 46 meters per second. Now notice that when we actually drop the equation, remember we had v equals square root of 2gh, where your initial velocity was 0. So just something to think about. Now, there's going to be another question over here. Go ahead and work on this question on your own. See if you can solve this question. Now, again, we talked about rate of power. Power is the rate of doing work, which is your work over your time, which is, we talked about the unit power is watts, which is how much joules per second. And we derived the equation for the power, which is your change in energy over your time, which is your force times your velocity. And that should, and then we talked about all this. We talked about kinetic energy, and we derived the equations for the kinetic energy. So here's another equation, here's another example. Go ahead and work on this example on your own. And that should actually finish chapter 7 for physics 111. If you have any questions, just email me at abunaem@uah.edu, or you can give me a call at 256-348-1480. Thank you and have a nice day.